This video lesson covers relative humidity with a focus on the measurement of relative humidity using a Sling psychrometer. Justin Wiseman is the original author of this lesson plans, with additions made by Derek Spencer. This video was made possible through the NSF-funded Boat of Knowledge in the Science Classroom project at Ohio University. How does a fan keep you cool? During summer, you find relief from the heat whenever a breeze of wind passes over you. When there's no air conditioning available, a rotary fan is the next best bet to cool yourself off. Why is this? Does a fan somehow cool air, or is something else going on? The air temperature isn't actually changing just because it's being moved by a fan. This cooling sensation has to do in part with the evaporation of sweat from your skin. To give you a long-winded explanation, your body has heat receptors embedded in your skin tissue, and on a hot day or during rigorous exercise, these receptors will send signals to the hypothalamus, which controls core body temperature. When you are overheating, the hypothalamus will activate sweat glands that secrete water and salts over the skin to help you cool off. Core body temperature regulation occurs through multiple modes of heat transfer: conduction, convection, radiation, and evaporation. When the temperature of the surrounding air is high and the relative humidity is low, the predominant mode of cooling is through evaporation. A fan works to cool your body by increasing the amount of air that is exposed to your skin, which in turn increases the rate of evaporation of sweat. Heat is removed from your body as sweat changes from a liquid to a gas, and thus cools you down in the process. This is known as evaporative cooling. We've all experienced that muggy, sticky, and sweaty feeling during a hot summer day, where no matter what you do, you can't get comfortable. Even a fan can't keep you cool. Under hot and muggy conditions, it is almost certain that the amount of water vapor in the air is high. We would say it is humid. But what determines how much water is in the air? Let's consider a typical daily temperature cycle. During the day, when the outside air temperature is higher, there is more energy available in the air, and liquid water evaporates at a faster rate than water vapor condenses. At night, when the outside air temperature begins to cool, there's less energy available in the atmosphere, and water vapor condenses at a faster rate than liquid water evaporates. The temperature at which water vapor condenses at an equal rate as liquid water evaporates is known as the dew point temperature. This is most evident in the morning hours and at night, when the temperature is equal to the dew point temperature. The water you see on blades of grass is from water vapor condensing out of the airstream. This is also the reason why water condenses on the outside of a cold can of soda on a warm, muggy day. The air temperature around the soda can has been lowered below the dew point by convective heat transfer from the soda to the air, and water vapor begins to collect on the surface of the can. It is important to note that the amount of water vapor in the atmosphere is a property of water, and it does not directly depend on the existence of other atmospheric gases. We saw previously how water moves between the liquid and gaseous phases under the influence of a change in atmospheric temperature. Now we will define some terms to help quantify water vapor concentrations in the air. Absolute humidity is a measure of the mass of water vapor in a given amount of air, typically expressed in grams of water per cubic meter of moist air. If we can measure the absolute humidity, the total mass of water in the atmosphere may be estimated to some degree. Typical ranges for absolute humidity values range anywhere from 0 to 30 grams of water per cubic meter of moist air. Absolute humidity does not account for air temperature. Relative humidity is defined as the observed water vapor pressure relative to the saturation water vapor pressure at a given air temperature. To be less technical, relative humidity is the ratio of the amount of observed water vapor to the maximum potential amount of water vapor that could be present at a given temperature. Relative humidity is an important parameter in determining how comfortable the local weather conditions are. That muggy feeling on a hot, humid day most likely has to do with a high relative humidity. Relative humidity is typically expressed as a percentage. The saturation vapor pressure occurs when a surface of water is in equilibrium with the air. That is, when the rate of liquid water evaporation and condensation are the same. Air is said to be saturated with water vapor when the air temperature equals the dew point temperature, or when the relative humidity is 100%. The saturation vapor pressure and dew point temperature are both dependent on ambient air temperature, meaning that their values will change with an increase or decrease in air temperature. These graphs depict saturation vapor pressure on the left and dew point temperature on the right as a function of air temperature. Dew point temperature is also highly dependent on relative humidity and increases as relative humidity increases. Thinking about it logically, more liquid water is able to evaporate through water vapor when the temperature is high, and this is reflected in the saturation pressure graph as saturation vapor pressure increases with increasing temperature. The dew point temperature should also increase when relative humidity increases. Water will condense more easily if it is saturated with water. Atmospheric water vapor plays a vital role in weather and atmospheric processes. It is the basis for the hydrological cycle, fueling our rivers and groundwater aquifers, and under extreme circumstances, it is involved in the formation of fog and virga. Fog can form when the air temperature drops near the dew point temperature, or when there is a sudden influx of moisture with little to no change in temperature. An increase in the amount of water vapor can occur when evapotranspiration rates are high or when warm, moist air passes over a cooler surface or area. Both of these processes increase relative humidity and can lead to fog formation under the right conditions. Virga is an odd phenomena where precipitation evaporates before it reaches the ground. This usually occurs in hot and less humid regions of the United States, typically in western states where there is little rainfall. Much like fog, high humidity is responsible for cloud formation. When hot humid air rises and cools below the dew point, water vapor condenses onto suspended particulate, eventually coalescing into large enough particles to form visible clouds. Precipitation occurs when water or ice droplets are large enough to overcome the buoyant forces from underlying air masses. In order to measure relative humidity, we need both the dry bulb and wet bulb temperature readings. The dry bulb temperature is a temperature we are most familiar with, and is a measure of the dry air temperature as measured with an ordinary dry bulb thermometer. The wet bulb temperature is measured using a thermometer with a wet gauze wrapped around the bulb portion. This allows for the consideration of evaporative cooling on a stream of air. As air passes over the wet bulb thermometer, water will evaporate from the wet gauze into the airstream, and the temperature of the thermometer will drop to compensate. Under high relative humidity, less water will evaporate, and there will be less difference between the dry and wet bulb temperatures. Under low relative humidity, more water will evaporate, and there will be a larger difference between the dry and wet bulb temperatures. Knowing the difference between these two measurements, we can use a psychrometric chart to determine the relative humidity. We will see later how to read a psychrometric chart. Now is a good time to conduct the lab constructing a Sling psychrometer. You will use a dry and wet bulb thermometer to construct this Sling psychrometer. A Sling psychrometer is a device used for measuring dry and wet bulb temperatures concurrently, and can be constructed using two ordinary thermometers. Each group of students will need two thermometers, one to measure the dry bulb temperature and another to measure the wet bulb temperature. To construct the Sling psychrometer, wrap dry gauze around the bulb end of one of the thermometers and secure with a rubber band. It is best to use thermometers with a hole or loop on the top end so you can secure a stiff wire to the end. Put the wire through the loop of both thermometers and secure tightly so they won't fall off if you spin them. To take temperature readings, wet the gauze on the wet bulb thermometer and start spinning. Check and record the temperature of both thermometers in 30-second intervals until you observe little to no change in temperature. This could take anywhere from 1 to 5 minutes. You may now pause the video here to perform the lab. To determine the relative humidity from your dry and wet bulb temperature readings, we can use a psychrometric chart. A psychrometric chart provides a graphical representation of the thermodynamic state of air at a given atmospheric pressure. In meteorology or air conditioning, the reference pressure is typically pressure at mean sea level. Knowing any two state variables of interest, we are able to determine the other variables. A psychrometric chart typically has lines corresponding to dry bulb temperature, wet bulb temperature, enthalpy, relative humidity, and the humidity mixing ratio. To find the relative humidity, draw a straight vertical line through your dry bulb temperature reading. This should be located on the x-axis. Next, draw a downward sloping line through your wet bulb temperature reading. In this example, I am using a dry bulb temperature of 30 degrees Celsius and a wet bulb temperature of 20 degrees Celsius. Finally, find where the two lines intersect to determine the relative humidity. Relative humidity lines on the psychrometric chart curve up towards the right-hand corner of the graph. It may be necessary to estimate the relative humidity by interpolating between two relative humidity lines if the intersection point of your wet and dry bulb temperatures falls between them. For this example, the relative humidity is nearly 40%. A simpler method of obtaining the relative humidity for this scenario is by using the chart on the left. The rows correspond to your measured dry bulb temperature, and the vertical columns correspond to the difference between your dry and wet bulb temperature. For a dry bulb temperature of 30 degrees Celsius and a difference of 10 degrees Celsius between dry and wet bulb temperature, the corresponding relative humidity is 39%. Again, it may be necessary to use linear interpolation to estimate the relative humidity for a more accurate result. Notice how the two results obtained using the psychrometric chart and the chart on the left are nearly the same. To summarize, our bodies produce sweat in order to regulate our internal body temperature. The evaporation of sweat cools your core temperature by removing excess heat as sweat changes from a liquid to a vapor. A fan increases the rate of evaporation by moving more air across your skin. Depending on the air temperature or available thermal energy in the atmosphere, liquid water will evaporate into the air or condense into a liquid. Water evaporates more during the day and condenses more in the morning and at night, when the temperature is close to the dew point temperature. Relative humidity is a measure of the ratio of actual water vapor in the air to the saturation water vapor which could be in the air at a given air temperature. The dew point is the temperature at which water will begin to condense. This is the point where the rate of evaporation is the same as condensation and corresponds to 100% relative humidity. Humidity also plays an important role in weather and in the formation of fog and virga. Measuring the dry and wet bulb temperatures of air, we can determine the relative humidity using a psychrometric chart.